Hello everyone. Today we're going to be talking about rigid transforms. This is subjects that are going to be covered in robotic systems, chapters 3.1 to 3.2. We're going to start by talking about two-dimensional rigid transformations. Let's imagine that there's some robot, let's say it's a mobile robot, and it has some geometry. This geometry is represented in some sort of reference frame. So we assume, for example, that let's say the x-axis is pointing forwards and then the y-axis is pointing to the left. But in any case, we have this kind of reference frame that stores some aspects of the robot, some points of interest that we know, and coordinates of those points of interest. Now, when we are looking at rigid transformations, we're thinking about what would happen if the robot were to go to a new location. What if it were to change where this reference frame is now located in the world space? So we're going to define some sort of world coordinate system, and we're going to define some set of parameters that tells us where the robot is actually located in this world coordinate system. So here we're going to have two parameters, tx, ty, describing the translation of the origin of the reference frame. This will be the reference point. And also an angle theta that defines how the robot is angled with respect to some reference direction. Typically, that's taking the x-axis of the reference frame and seeing how that x-axis has been oriented with respect to the world frame. So let's call the reference frame T0, and let's call the robot's current frame T. So we'll want to ask questions like, if we have a point that we know that's on the robot's geometry, let's say it's a camera location, or maybe it's the location of the front left bumper of a vehicle. So this point P, it moves while attached to the robot. Now, we know its local coordinates. These are coordinates that we've measured somehow through some sort of calibration process, or we've measured it through a ruler, and we know where it is in the reference frame. But now that the robot has moved somewhere in the world, we want to now figure out how are we going to measure the world coordinates of this point. Now, what it means by world coordinates, we want to figure out where, with respect to this world frame, this point actually lies. And there's a lot of good reasons for that. For example, collision detection, proximity detection, and so on. So we're going to think about this in two stages. So we're going to take the robot and its original reference frame. We're going to align that to the world coordinate system. And then we're going to first rotate the robot about the origin point by the angle theta. Then we're going to translate the reference point to tx, ty. So thinking about this point and its original coordinates p0, it's first going to be rotated to some new coordinates p1. We'll talk about how to get to these coordinates in just a bit. Next, we're going to do a translation, and this is rather simple. So we're just going to translate by tx, ty, and this is basically just a vector addition. So the resulting point that we get is p2, and this is just p1 plus the vector t. Okay, so let's talk about the rotation component first. So if we're to think about rotations in two dimensions, this is the simplest case. We're going to get into 3 dimensions later, which is a bit more complicated, but let's start with a simple case first. So let's rotate by this angle theta. If we're to think about this coordinate frame, let's actually take some, we can either take our fingers as our coordinate frames, or we can take some two pens or pencils as coordinate frames. We just want to think about rotating them by some amount. And if you're to imagine not just the rotated coordinate frames, but also the original coordinate frames overlaid on top of each other, we're actually trying to figure out where are the new coordinate axes with respect to the original coordinate frame. So let's think about the x-axis of t0. Once it's rotated, it now has coordinates given by this x vector cosine theta, sine theta, if you just remember your elementary geometry. The y-axis has coordinates negative sine theta, cosine theta. So from these two coordinates of the new x and y axes, we can then compute how the points in this coordinate frame t0 are transformed after getting to frame t. So px and py are the coordinates of this point P. So as we rotate the frame t0, since we know that this point is attached to that frame, we can represent the coordinates px and py as coefficients multiplying the x vector, the x-axis and the y-axis of the original frame t0. So these coordinates px, py get rotated to the coordinates px times the x vector plus py times the y vector's coordinates. So now if we just compute this all together, we end up getting these equations, which gives us the ultimate form of the expression of rotation, px cosine theta, py sine theta as being the x coordinates of the new point, and px sine theta plus py cosine theta being the y coordinate of the new point. Now, if we were to squint at this a little bit, we can find that if we take the p coordinates and try to pull it out of this equation to actually recover the p vector, we can recover it as a matrix vector product, where this expression gives us a 2x2 matrix times a 2x1 vector, which is the original point coordinates. So this matrix here is special. This is going to be called the 2x2 rotation matrix of an angle theta, and we'll denote it as r of theta. So this is a function from angles to 2x2 matrices. And you can another way you can think about this is that given this 2x2 matrix, the first column of the matrix tells us where our x vector has rotated to, and for the second column, it's where the y vector has rotated to. Okay, so now let's think about the rigid transformation component. We've rotated, now we're going to do the translation. So we're going to just add this together, this translation component onto the rotated point. So to put it all together, we're going to define this rigid transform operator. So t of r and the translation t, this is a function that takes points that are in the local coordinates t0, and they're going to be translated and rotated into the world frame, and it's going to be given by this sequence of a matrix multiplication between r and p plus the translation t. Okay, hopefully simple enough. All right, now let's get into a more complex case. So let's look at 3D. In 3D, the case is very similar. Instead of having a 2x2 matrix, though, we have a 3x3 matrix. And here we're going to assume a right-handed coordinate system. You have the best coordinate system right at your hand, so you think about your right hand. If you want to think about this, you can consider your thumb as the x-axis, the index finger as the y-axis, and then your third finger as the z-axis. So this is a right-handed coordinate system. It might be flipped in the video here. And in any case, what happens is that the coordinate system, you can also, if you want to use colors, there's actually a mnemonic here where the red is the x-axis, green is the y-axis, and blue is the z-axis. And when this then rotates, this is basically how it rotates. And so what we're trying to do when we represent this rotation matrix is that if we think about the original coordinate frame here lining up, and then the new coordinate frame of this new frame, and we think about the coordinates of each of the axes. Let's start with just one of them. So in that pose, we had the x-axis, and here's my right-handed coordinate system. The first column of this rotation matrix, r11, r21, r31, those are going to be the coordinates of this point, of this axis, in the world reference system after the rotation. Same thing for y and z, just with the second and the third columns in this matrix. Okay, so just like in 2D, if we want to perform a rotation of some point in a local coordinate system and convert it to the world coordinates, we just simply perform the matrix vector multiplication. So given points, this point here with x, y, and z here is 0, what we're going to do is think about each of the columns of this matrix as vectors, and each of those each of the coordinates of this point stays the same. So the amount that this point moves along the x-axis stays the same, it's just that the x-axis has changed. And so this gives us x times the first axis. So we can start by thinking about how much this thing has moved along the x-axis. We can think about how much the coordinate is shifted along the y-axis, and we can add those two things together to get this point here. And if we're to compute this final result here, we'll actually get the coordinates of the point in the world coordinate frame. All right, so this is simply the matrix multiply r times xyz. Okay, so fairly straightforward. And the rigid transformation in 3D is pretty similar to in 2D. Here, just the only difference is that R is a 3x3 rotation matrix, and the t vector is a translation of 3 coordinates. And just as before, when we want to do a rigid transform of a local point, we get its world coordinates by multiplying by R and then adding the t vector. Okay. So transforms are going to be used throughout this course. We use them ubiquitously throughout robotics. And there's many different types of operations that if you want to be a good roboticist, you really need to know really well about how to operate on these transforms. So the first 3 types of operations are application, composition, and inversion. These are accomplishing changes of coordinate frame. So if we have coordinates represented in terms of quantities in one frame that we know, and we know the transformation from one frame to another, then we can get the quantities in terms of the other frame's coordinates. So application we've already seen, so we'll check that off. Now let's start to look at the composition and inversion operations. There are also operations that we'll look at in the future with interpolation and differentiation, which represent movement, but those are going to be left for a future lecture. Okay, so let's think about composition. So we're going to assume that we have a first transform where we have, let's say that we, here's an example. So if we know where a camera is located on our, let's say, a mobile robot, we can represent the frame of the camera. Let's say a point that's, the origin is at the center of the camera. Let's say it's my eye, for example. So here you can see my head here. So I have some coordinate system where the origin is my eye. It has some direction that's forward. Let's call it the z direction, some direction that's right, and then some direction that's up or down. And so this gives us a coordinate frame. So my head also has a coordinate frame. And if I were to think about where my eye is going to be, if I'm walking around in my space, if I know where my head is located, and I know its frame, and if I know the local coordinate frame between my eye and my head, I can now figure out where my eye is and how it's oriented with respect to the world frame. Okay, so this first transform here is going to be the eye to the head transform. So if we think about, if I see a point somewhere right ahead of my eye, then that's going to be a point in my visual field that has some local coordinates. The transform here is going to transform the point to my head coordinate system. Now let's suppose that that transform is then followed by another transform. So my head is now moved to another location from its reference point. So if we're to compose these two together, what do? Well, the result of the point from the first transform becomes the local coordinates of the point for the second transform. So this is a function composition. We perform the first operation and then the second operation as follows. So you can see that the t of theta prime, t prime, that transform is on the outside. The second transform is on the outside. The first transform is on the inside. This can be rather confusing because we're used to thinking from left to right, but here the operations are actually performed from the right to the left. Right. Now, if we just go ahead and take the kind of normal expressions of these transforms, we can expand them using standard linear algebra. And because matrix multiplication is associative, we can regroup these terms such that the first term is a pure rotation term multiplied by the original coordinates p. And then the second term is a translation component. So what this means is that this whole composition of these two transformations is equivalent to applying a single rigid transform where the representations are basically functions of the original representations. So t double prime here is equal to r of theta prime times t plus t prime. Theta double prime, the ultimate reorientation, the ultimate angle that this composed transformation rotates is simply the addition of the two angles. Right? If you imagine rotating some angle and then rotating another angle, the overall rotation is the sum of those two angles. Now, we did a little bit of magic there, actually. So if you looked at the r theta prime times r theta, it's not immediately clear that that's actually equal to the rotation of the sum of the two angles. So let's go ahead and figure out how we actually got this. So if we're just to perform the matrix multiply of these two 2x2 matrices, we'll get the following expression over here. So these are just performing the standard matrix multiplies. Here we have a 2x2 matrix as the result, and the entries of these terms are the cosines and sines of theta 1 and theta 2. So if we're to actually perform these operations, then you can see that the diagonal here actually turns out to be equivalent between these two matrices. If you notice that the rotation matrix has cosine theta, negative sine theta, cosine theta in each of its entries. So it has the diagonal being constant, or not constant, but equal. It's uniform. And then the diagonals are actually negated from one another. And you find that actually when you compute this, it becomes the same thing. So the diagonal of this composed rotation becomes cosine theta 2 times cosine theta 1 minus sine theta 2 times sine theta 1. And if you remember some of your geometry in the past, you'll see that this is cosine theta 1 plus theta 2. This is the angle addition formula. And if you do the same thing for the off diagonals, you'll find that this is negative cosine theta 2 times sine theta 1 minus sine theta 2 cosine theta 1, which is equal to sine theta 1 plus theta 2. Negative sine theta 1 plus theta 2, sorry. And so this proves that the composition of these two matrices is simply the rotation matrix as a function of the sum of the two angles. Incidentally, this also proves a lot of other nice things. So first of all, the rotations in 2 dimensions are commutative, so you can switch the order of the operations and it doesn't matter. Moreover, the rotation of the negative of an angle is the inverse matrix of the rotation matrix of the angle itself. So, but you also see that if you just negate the angle, you just get the transpose of the matrix. So a 2D rotation matrix's inverse is also its transpose. Okay, a lot of great facts can be proven through some analysis here. Now, moving to 3D, the situation is very similar. So just performing essentially the same operations as before, we can get a rotation component. If we follow these two transformations, we get a rotation component times the original coordinates plus a translation component given by this formula here. So this here shows that the composition of two 3D transformations is also a 3D rigid transformation, and you get these results as follows. But note here that we don't have necessarily that these two matrices, R prime and R, they're not commutative. This matrix multiplication is not necessarily commutative. We've shown that it is the case in 2D, but it's not the case in 3D. So be very aware of that whenever you're doing operations on these expressions. Make sure that you get the order of operations correct. Okay. So, but a couple of other properties of 3D rotation matrices hold. We're not going to prove all of these, but basically if you, these are well-known facts. So first of all, the determinant of any rotation matrix has to be 1, positive 1. It's also a matrix that preserves length. So if you multiply any vector x by a rotation matrix, the length of that vector remains the same. The transformed vector is the same. Moreover, the product of any two rotations is also a rotation, and also the rows and columns of the rotation matrix are also orthogonal. So this also means, though, that the rotation matrix's inverse is also its transpose. So basically, if we wanted to take this point and convert it back into local coordinates, we can just multiply it by the inverse transform, or the transpose of R. Both of those are equivalent. Okay. So now rigid transformations also have inverses. Turns out that they are also rigid transforms, and just for the sake of time, we'll show that just give the equation here about how you invert the transform. So if you had y is equal to a rigid transform of some point x, then x is also a rigid transform of a point y with the inverse rotation and some rotated and negated transform. The proof here is left as an exercise. Okay, so we basically checked off the first three basic operations for transforms: application, composition, and inversion. Just to give a quick note about a practical issue when applying transforms in practice is that you have to be really careful about what you're transforming. So let's take a frame, and we want to convert local coordinates of a point to the world. Well, we just do the rotation and affine translation as we've discussed so far. That gives you the point that we're trying to measure the coordinates of in the world coordinate system. However, if we wanted to take a directional quantity, let's say like the velocity of this robot, or maybe a force that we're applying, or perhaps a displacement between 2 points, these don't get affected by the affine translation. So they only get affected by the rotation part. And so this vector here, which is rotated on the bottom right, that's these coordinates here, the x and the y here, those are the correct measurements. However, if we added that translation component, we'd get this incorrect vector here, right? So you really don't want to do that. You really want to be careful about what you're doing for these rigid transforms. And we'll talk about various ways of doing that when we talk about homogeneous coordinate systems. Okay, but in general, just mind your P's and your D's, your points and your displacements. Okay, so as a recap, we represent coordinate frames with these rigid transforms. The application of a rigid transform takes local coordinates of points to world coordinates of those points. You can also apply them to directional quantities, although you omit the translation component. We can compose rigid transforms, we can invert them. The inverse of a rotation matrix is its transpose, both in 2D and 3D. Composition of rotations is commutative in 3D, but not in 2D, but not in 3D, and rigid transforms are not commutative in general. All right, thanks. See you next time.